So we've got our usual wave equation, amplitude times sine of 2 pi times time over period, plus or minus 2 pi times position over wavelength, plus some phase constant. Oh, and there could also be a plus equilibrium height also, which I think we are going to need in this one. So let's say we want to find this equation, all the values in the equation from these two graphs. And first of all, why do we need two graphs of the same wave? What's the difference between these two graphs?
One's a y versus x and one's y versus t.
Yeah, and a very useful way to think of those, if we're talking about y versus x, we're looking at all positions. But all positions means we're only looking at one time. So how would you interpret that? If you're looking at all positions but only one instant in time, what does that suggest? Or what might we call that?
A snapshot of the entire wave.
Yeah, this is usually described as a snapshot of the wave in the sense of, like, if you watch this wave passing by on, maybe it's on a rope or maybe it's the surface of a lake or something, we're just taking a single instant in time, maybe taking a picture of the surface of the water at that instant. Or you could also think of this as like you've got a video of the wave passing by and you hit pause at some instant in time. This shape is a freeze frame, single paused instant of the shape of the surface of the water at that moment in time, at time 2 seconds, or whatever is marked up here. Whereas the other graph is showing all time, but at only one location, x equals 10 meters. So the time graph I tend to think of as a history describing what's going on with that one location. As the wave passes by, we're watching just one location as it bobs up and down. Like if you've got a wave on a rope, imagine you've like tied a little marker to that one spot and it's just bobbing up and down. Or waves on the surface of a lake, maybe you've got a boat or a buoy or something at this one point, and it's just bobbing up and down as it floats as the wave passes by. So this graph is keeping, the second graph here is keeping track of the height of that buoy as it bobs up and down as time passes. Which also means on this graph, don't think of this axis as left and right. Think of it as past and future, because that is a graph of time. With that in mind, let's see if we can if we can find values for any of these numbers here, because we need to find the amplitude, the period, the wavelength, the phase shift, the equilibrium height, and also whether this should be plus or minus. So what can we start with? What information can we pull directly from these graphs?
Amplitude.
Yeah, we should be able to get amplitude. And how could we measure amplitude here?
At one of the peaks of the wave.
Yeah, if we take a look at a peak, for instance, it looks like this goes as high as 60 and also as low as 10, I believe. So if the highest point is y equals 60 and the lowest point is y equals 10, what would the amplitude have to be?
25.
Yeah, it should be 25 because the amplitude is half of that. The distance between the highest and lowest points is 50, but amplitude isn't the distance between highest and lowest. It's the distance between the equilibrium center line at lowest. So the amplitude is going to be half of that 50 difference. So half of 50 would be 25. That's the amplitude we're talking about. So amplitude is definitely going to be 25 here. And that might have units attached to it. Presumably this is y measured in meters or centimeters or something. Since no units are given, let's just call that unitless, 25. So amplitude will be 25. What else can we get from this graph? Actually, what is that center line going to be? What's that midpoint that it's oscillating above and below?
That's y naught.
Yeah, and what is the value of y naught here?
35, I believe.
Yeah, it looks like 35. I mean, from the graph, we can see it seems to be halfway between 30 and 40. More accurately, we can say it's amplitude above the low point, so 10 plus 25, or amplitude below the high point, so 60 minus 25. Either way, you get to 35. You can also find it directly from the highest and lowest points by just taking the average. The average of 60 and 10 is 35. So we can fill that in as well. And that leaves us with period, wavelength, phase shift, and plus or minus to decide. Any thoughts on how we could find any of those pieces of information? For instance,
is the wavelength,
hmm?
oh, sorry, is the wavelength 11? I think so. You can find it between the two peaks in the Y versus X graph.
Yeah, if we look from peak to peak on the Y versus X graph, do we have coordinates of two peaks? Looks like we have a peak here at, looks like 11, though it's kind of difficult to tell if that's exactly 11. Is there a peak at 0? If we zoom in on that, does it look like it has actually reached a peak when it gets to 0?
Yes, or are you not able to assume that?
It's kind of difficult to tell because it looks like it's a peak should be when it reaches 60. It looks like it's not quite at 60 here. And it's kind of difficult to tell there. I think we can't necessarily say that's exactly a peak. I wouldn't really want to count on that. It looks like we definitely have a trough here, though, at looks like 5 and a peak at 11. How far is it from 5 to 11?
6. So then we can just multiply that number by 2 to get wavelength.
Yeah, exactly. This distance here from 5 to 11 is half of a wavelength. Anytime you're going from, because wavelength is from crest to the next crest. If you're just going from trough to crest or from crest to trough, that's half of a wavelength. So one thing we can do here is we can say half of a wavelength is equal to 6, and let's say these units are marked in meters. So if we say half of a wavelength is 6 meters, we can just multiply both sides by 2 and get 12 meters. So it looks like the wavelength should be 12 meters. And even if we're not sure about the 5 and the 11 exactly, because those are not really clearly marked, another thing you can look for is the equilibrium values. For instance, 2 here, I think we can definitely say this, it's passing through equilibrium on the way down at 2, because that's actually marked. What would be one full cycle beyond that?
At around 14.
Yeah. 14 is the next time it's equilibrium on the way down. And for points other than crests and troughs, you want to be careful about that. Because it's tempting to say, well, here's equilibrium, here's the next equilibrium. Why is that not one full cycle, though? What's the difference between those 2 points? Can we just say this is equilibrium, so they're the same type of point? What's different about them? Or what do you notice about the slopes of those 2 points?
One's negative and one's positive.
Yeah, we've got equilibrium on the way down and equilibrium on the way up. Those do not count as the same type of point. So you could say from equilibrium on the way down to equilibrium on the way up, that's half of a cycle, half of a wavelength. So once again, you could say wavelength over 2 equals 6 meters from 2 to 8, and then double that. Or you could, since we have enough of the graph here, you could say, here's equilibrium on the way down, and then the very next equilibrium on the way down. That really is one complete cycle. So from 2 to 14 is one full cycle. Once again, that tells us wavelength is 12 meters. So either way, we get 12 meters as the wavelength. And then we can use a similar approach on the time graph to find what other information.
Period.
Yeah, we can find the period here. And in this case, we have even less of a complete cycle to work with. We don't really even have a graph of a complete cycle. It looks like some points we can mark, though. We have, for instance, equilibrium on the way up at 1 second, and then a crest at 2.5 seconds, then equilibrium on the way down at 4 seconds. Or let's say we just use this equilibrium on the way up, or equilibrium on the way up and the peak, 1 second and 2.5 seconds. How much time is that?
One and a half.
Yeah, 1.5 seconds equals, and then what fraction of a full cycle is that? If we're just going from equilibrium to the peak.
A fourth.
Yeah, so we can say 1.5 seconds equals a fourth of a period. And then the period would be how much? How would you isolate t here?
It would be 6 seconds.
Yeah, multiply by 4, you get 6 seconds. So the period should be 6 seconds. And so even if you're dealing with a situation where you have not enough of the graph shown to get one full cycle visible, you can still often identify a specific portion of a cycle, a specific fraction of one period or one wavelength, and work it out from there. This is also sometimes a useful approach if the wave is oscillating like too quickly to really notice. Like if you have a graph that looks like this, maybe the axes are labeled too far apart for that to really be useful. Like maybe you've got labels here and here and here. Maybe this is like 1, 2, and 3. In a case like that, it can be difficult to pin down one full cycle, because one full cycle would be something like this. And that can be difficult to measure. But if you look at this in terms of several cycles, we can say, for instance, we've got one full cycle, and then another full cycle, and then another full cycle. So that's how many cycles in how much distance.
That's 2 cycles.
Looks like we've marked 3 cycles here. There's the first one, then this second one. So from equilibrium on the way up to the next equilibrium on the way up, and then to the next equilibrium on the way up, and then to the next equilibrium on the way up. So that's 3 cycles, let's say 3 lambda. And how much distance is it? If we're going from here to here.
2.
Yeah, and if that's a distance, let's say 2 meters. Even though we can't easily identify what one full cycle is, we can say 3 cycles is 2 meters of distance. And then once again, you can solve for lambda by dividing by 3 and get 2/3 of a meter. So that's another approach that's often useful. If the waves are squished too tightly in with each other to easily measure exactly one, but maybe you can measure like from here to here as a known distance and count how many waves fit in that space, and then divide to find the wavelength. So that's another approach that's often useful if the waves are too bunched in on each other to measure easily. Any questions on measuring those parameters so far? Fill in the values we have. We know period is 6 seconds. We know wavelength is 12 meters. So what mysteries do we still need to unravel here? What else is still unknown about these graphs?
The phase constant.
Yeah, we still need to know the phase constant. And the phase constant, phi, is usually the very last one you find. Because the other ones you can measure directly from the graph, the amplitude, the period, wavelength, but phase constant does not really easily show up visibly on the graph. Also, one other thing we need to figure out before that, we still need to figure out if this is plus or minus. So how do we do that? What does the plus versus minus signify in this equation?
If it's moving to the left or right.
Yeah, so we're going to need to discover which direction it's traveling. And to do that, in order to figure out anything about direction of travel, motion involves position and time. So we're really going to need to combine both graphs here, the time graph and the position graph. And to do that, we need to start by identifying a point they have in common. In other words, the same information on both graphs. And that's tricky to do because one graph shows all positions, but only one time. The other graph shows all time, but only one position. But we can use that to our advantage. What's the only time shown on the top graph?
T equals 2.
Yeah, that whole graph is at t equals 2. But we can find t equals 2 on the other graph. T equals 2 is this one point on the graph. So that one point is t equals 2. Let me label that with its actual coordinates. We've got this location is t equals 2, x equals, what's the x value for that point? In fact, yeah, the x value for this entire graph is 10. And then the y value, kind of difficult to tell exactly, but looks like around 55. So that means this point has coordinates t equals 2, x equals 10, y equals approximately 55. Can we find that same data point on the x graph? Because remember, this entire time graph is also only at one position, x equals 10. Can we find x equals 10 on the x graph?
We can find it by looking at the 10 value on the x-axis on the top.
Exactly. We've got 10 on this graph right here. So the coordinates of this point would be t equals 2 because this entire graph is t equals 2. X equals 10 because that's the coordinates at that point on the graph. And it looks like y is about 55. So these 2 points that we've marked here are the exact same point. They're just marked in, they're just displayed in different ways on these 2 different graphs. Any questions on that so far? The one point the graphs have in common. So now that we've identified that, we need to figure out what's happening next. Because remember, the x graph we could think of as the shape of the entire wave, but paused at one instant in time. We want to know what happens when you press play. Does the graph shift to the left or to the right? And to do that, if we want to know what happens next, what graph should we be looking at? If we want to know what happens a little ways in the future, which one of these graphs shows the future?
Y versus t.
Sorry, what was that?
Y versus t.
Yeah, the y versus t graph shows past and future. So if we take a look at into the future, again, from this point, the t equals 2 point, If we go a little ways into the future, is that point on its way up or on its way down?
It's going up.
Yeah, this point is on its way up. As we go a little ways into the future, this point is on its way up because of the positive slope. So that means we can be more specific. We can say at t equals 2 and x equals 10, the y value is 55 and rising. That point is on its way up. And that's true for the x graph as well, because this is the same data point. It represents the same information, just displayed a different way. And it's the same wave. We're just talking about one wave here. So we know as time passes, this point must be on its way up. So let's try drawing this out. If we have this shape of wave, and let me draw this so we can move it around. This shape wave like so. And we have the options of moving this graph to the left or to the right. And we want to make absolutely sure that this data point is on its way up. Which direction of moving the graph would allow this data point to move up?
If you move it to the left.
Yeah, if we move the graph to the left, then that pushes this data point upwards, so it stays on the curve. So that tells us the graph itself, the wave is moving to the left. On the other hand, if we had thought, well, maybe the wave is moving to the right, that would cause this data point to sink to match the wave as it moves to the right. So it can't move to the right because we know that point is moving up, not down. Another convenient way to think of this is if you want this point to move up, is up associated with a trough or a crest?
With the crest?
Yeah, so if we want this point to move up, then we should expect the nearest crest to move towards it. And for this crest to move towards it, the crest would have to be moving to the left. And in fact, the whole wave would be moving to the left. So it looks like this wave has to move to the left so as to force this point upwards, as shown by the positive slope on the t-graph. Any other questions on that so far? All right, so if we know it's moving to the left, the negative x direction, should we use plus or minus in the equation?
Plus.
Yeah, that should be plus to balance out the negative motion. So at this point, we should now have everything except the phase constant. That's the one unknown left. And any thoughts on how we could find that phase constant, that phi value?
We can choose a time or like a crest and then plug in those values because we know the argument of sine will be equal to pi over 2.
Yeah, that should work. If you take a look at what's inside the sine function, if you're looking at a crest, then what's inside the sine function has to be pi over 2. If you're looking at a trough, then what's inside the sine function has to be 3 pi over 2. And that stuff inside the sine function is usually called the total phase, usually written as a capital phi. Total phase, everything inside the sine function. And this is just a convenient way of writing out the whole thing inside the sine function, usually written as a capital phi. Let me go copy paste one of those. So capital phi, the total phase, is 2 pi t over period plus or minus 2 pi x over lambda plus little phi. And that just represents shorthand for everything inside the sine function. And generally, if you're at a crest, you can expect the total phase to be pi over 2, because sine of pi over 2 is the highest it can get. If you're at a trough, you can expect the total phase to be 3 pi over 2, because sine of 3 pi over 2 is as low as it can get. Or alternatively, you could use negative pi over 2. That also works. So if we know we're at a crest or a trough, you could, in theory, use other points on the graph, but crests and troughs are most convenient, largely because there's only one crest in each cycle and only one trough in each cycle. So it avoids the ambiguity. So what is a crest or trough whose coordinates we know here?
We know at, if we look at the y versus x graph, at x equals 11, we know time is equal to 2.
Yeah, let's use that. We definitely have a crest at this location. So crest at x equals 11 meters, time equals 2 seconds. So that means we can fill in 11 meters for x, 2 seconds for t in the total phase equation, and set that equal to pi over 2 because it's a crest. So we'll fill in those values. Time is 2 seconds. Position is 11 meters. And if we can simplify this, it looks like phi, little phi, the phase constant, is the only unknown left. So we should be able to solve this algebraically for phi. To start with, let's simplify a bit. It looks like the units cancel out nicely. We've got seconds and seconds cancel out, meters and meters cancel out. So we've got 2 times 2 over 6 reduces to 2/3, or 2 pi over 3. And then 2 and 11 reduces to 1/6. So 11 pi over 6 equals pi over 2. And also plus phi, I won't forget that. And how do we combine the 2 pi over 3 and 11 pi over 6?
Have a common denominator of 6.
Yeah, so let's go ahead and put that 2 pi over 3 back to 4 pi over 6. Add those together, we get 15 pi over 6. And we may as well write pi over 2 in terms of sixths also, 3 pi over 6. And then how would we isolate phi?
Can just subtract 15 pi over 6 from both.
Yeah, and 15, or 3 minus 15 would be negative 12. Looks like that reduces to negative 2 pi. So that's a phi value we can use. Any questions on that so far? And one other thing we can do, what can you always add or subtract to an angle that doesn't really change the angle?
2 pi.
Yeah, you can always add or subtract 2 pi. So negative 2 pi would work, but it's usually more convenient to have a non-negative phi value. So let's add 2 pi to that. You can always add or subtract any whole number multiple of 2 pi to the phase shift. It looks like we end up with just 0. So that suggests we don't actually need a phase shift here. The phase shift is just going to be 0. So we can fill in plus 0 here. We could just leave that out. I would actually go ahead and write it as plus 0 just to confirm, to make it obvious to whoever's reading it that you really did get 0 as the phase shift and didn't just forget to write in a phase shift. But it looks like the phase shift here is 0. Any questions on that? And it looks like that is our final answer here. This is we set out to find the equation of this wave, and that's exactly what we have. And you could now use this, for instance, if you wanted to know the height at any position at any time, you could plug in any number of meters for x, any number of seconds for t, punch that into a calculator, and that'll tell you the height of the wave at that position at that time. Or alternatively, you could create other graphs. Like let's say you wanted to make a new t versus y graph at x equals 15 meters. Plug in 15 for x and you get y equals a function of just t, which you can then graph. And that'll be the shape of the wave at x equals 15. Or I guess I should say the history of the wave, since it's a t versus y graph. Any other questions on that one?
Can you also, instead of using the total phase equation, just have plugged in for, if you did like y of x comma t equals the whole equation, couldn't you just plug in values for x and t there?
Yeah, that would also work. You could go back to the whole equation, plug in 11 for x, 2 seconds for t, and then plug in 60 for y, because that's the y value at that point. But the thing is, if you did that, the very first thing you would do would be subtract 35 and get 25, divide by 25 and get 1, and then take the inverse sine of 1 and you get pi over 2 anyway. So it gives you the same result. It does add a few extra steps, but if it feels more intuitive to do it that way, then go for it. It's just that the total phase equation, or using the total phase instead, is a very convenient way of skipping a few of those steps. And also part of the reason why they're introducing the idea of total phase is that it's going to be very important when we get to interference of waves later on. When you have like several waves occupying the same space and either combining or partially canceling out, it's useful to know what the total phase of each one is, because the total phase is usually how we compare, are these two waves both at a crest at this point, or are they both at a trough, or is one at a crest, one at a trough, or somewhere in between. So certainly use the whole equation to solve for phi if that makes more sense to you, but also don't neglect the idea of total phase. Make sure you understand what total phase is in terms of representing what point of the wave are you at, because we're going to be coming back to that later as well.
Got it, thank you.
Any other questions on that example? If you have two x graphs or two t graphs, let's try out an example of that also, because it turns out it's mostly the same procedure, except you need to go about finding the process of finding the direction of travel is very different. So let me pull up an example we can use for that. Okay, can you see this new pair of graphs with two x graphs?
I think we still see the old one.
Okay, let me see if I can get this one. How about now?
Yes.
Okay. And one other thing about if you're dealing with two position graphs or two time graphs, like I mentioned earlier, direction involves a direction of travel. Anything involving motion involves position and time. So if you have two time graphs or two position graphs, that alone is not actually enough information. You do need one piece of information about motion, usually in the form of speed. So let's say we are given that the speed of this wave is 2.5 meters per second, and these two position graphs. By the way, what determines the speed of a wave? Why does a wave have a certain speed?
It's determined by the frequency and the wavelength.
It's related to the frequency and the wavelength in the sense that speed equals wavelength times frequency. But you can't really choose the wavelength. When you're shaking one end of the rope, you get to choose the frequency. But yeah, the medium is ultimately what determines this. The only thing that determines how fast a wave travels is the properties of the medium it's in. Like if you're holding one end of a rope and you're shaking it, the speed at which the pulses travel depends only on the properties of the rope itself, specifically the rope's density and tension. If you shake the rope faster, or if you make the pulses larger, that does not change how fast the pulses spread out. The only way you can change how fast the pulses spread is by changing properties of the rope, either by swapping it out for a heavier rope or lighter rope, or by stretching it tighter or giving it more slack. Only the properties of the medium itself determine the speed of the wave. Same thing for sound waves, for instance. If you're talking and your sound reaches the other end of the room, you can't make your sound get to the other end of the room faster by shouting louder. The sound still takes the same amount of time to travel. The only way you can change how fast the sound spreads are by changing the properties of the air that it's traveling through. Typically either changing the temperature of the air or changing the density, the gas makeup, like changing humidity, for example. But you can't, as the source, you cannot change the speed of the wave. That's determined entirely by the medium. As the source, you do get to choose the frequency. You can choose, like again, for shaking one end of a rope, you get to choose how many times it oscillates per second. So you do get to choose the frequency. And then the wavelength is sort of determined by the speed and the frequency together. Any questions on that so far? All right, let's see if we can piece together the direction of travel here. We've got two x graphs. So what can you measure directly from the x graphs?
Wavelength.
Yeah, you can measure wavelength directly. For instance, here you can measure just, let's say, from 4 to 10, 6 meters. So wavelength is 6 meters. And you can't directly measure period from a position graph. But if you know wavelength and speed, you can calculate the period based on the fact that speed equals wavelength divided by period. So you can find the period if you already know speed and you can measure the wavelength. Or vice versa. If you had two time graphs, you can measure period directly and then calculate wavelength algebraically. But the important one to consider here really is direction of travel, because that's really the trickiest one, I think. Everything else you can measure directly or calculate algebraically. You can't really find a point in common here because everything on the first graph is at what time? Yeah, the entire first graph is 6 seconds. We can't just look for 6 seconds on the other graph because the entire second graph is at a different time, 10 seconds. These graphs represent what the wave looks like at two different instants in time. Like you got the wave traveling, again, let's say you have a video of the wave traveling. You hit pause at 6 seconds and draw what it looks like. And then also you hit pause at 10 seconds and draw what it looks like. But then you come back to it and you only have these two freeze frames. You need to figure out from those two freeze frames which direction it's traveling. And typically what you want to do there, instead of looking for a pointed common, you want to look for maybe a crest on one graph and a crest on the other graph somewhere else that's really the same crest. Or a trough on one graph and a trough on the other graph that's really the same trough. And I usually pick one near the middle to focus on. So that way it might go either direction, we don't know. But either way it goes, we can keep track of it. Like let's say we're looking at maybe the trough at 7. There's definitely a trough at x equals 7. At time 6 seconds. What we want to know is which trough in the other graph is the same trough at 10 seconds. And how much time passes between those graphs? Because so far we don't know if that's the same as this trough or this trough, this trough. Yeah, these graphs are 4 seconds apart. we know that we have a picture of what the wave looks like at a certain instant in time, and another picture of what the graph looks like 4 seconds later. And if we want to know which one of these other troughs actually matches up, we need to know how far that travels. 10 meters, yeah, that should work. And how do you know it's 10 meters? Right, if we go back to the original definition of velocity, velocity means distance over time. In this case, we know the velocity is 2.5 meters per second. We don't know delta x, but we do know that delta t is 4 seconds because there's 4 seconds of time passing between this snapshot and this snapshot. So you can solve for delta x. Multiply both sides by 4 seconds. 2.5 times 4 would be 10. Seconds cancel out, so we get meters. So what we need to do is look for another trough that's exactly 10 meters away from 7. So it's 10 meters ahead or 10 meters behind. And in this case, maybe the middle isn't really the best one to pick because we can't really look 10 meters ahead or 10 meters behind are both going to be off the chart. But we can still use the idea that we want to find 2 crests that are 10 meters apart or 2 troughs that are 10 meters apart. So can you identify a crest on one graph and a crest on the other graph that are 10 meters apart? Or a trough on one graph and a trough on the other graph?
The trough at t is equal to 6 and x is equal to 13 on the top graph, and t is equal to 10 and x is equal to 3.
Yeah, those look about the same. Because if this is a trough at 13 and a trough at 3, those 2 locations are 10 meters apart. And we know that the wave is going to be traveling 10 meters in these 4 seconds of time. So this is a way to find not exactly a point in common because they are different coordinates, but at least the same trough on both graphs, or maybe the same crest on both graphs. For instance, maybe 10 and 0 would also work. But now that we've established the same trough on both graphs, or the same crest on both graphs, let's write this out. 4 seconds later, there's the same trough at x equals, let me modify that one, crest at 13 meters, and this, or trough at 13 meters, and the same trough at 3 meters at time t equals 10 seconds. So we know that the trough hits the 13 meter mark at 6 seconds, and the same trough hits the 3 meter mark at 10 seconds. So let's see what that's going to look like. If we've got this medium and we've got a trough hitting the 3 meter mark and the 10 meter mark, or sorry, 3 meter mark and 13 meter mark. So we're essentially just drawing an x-axis here. We know that it hits the 13 meter mark at time 6 seconds. And that same trough hits the 3 meter mark at time 10 seconds. Now that we've got that information, which one of those events happens first? Yeah, 6 seconds is an earlier time than 10 seconds. So if it hits if it hits 13 meters earlier and then later hits 3 meters, which direction has it moved?
To the left.
Yeah, exactly. This trough, and in fact, the entire wave is traveling left. So we can tell from that information, this whole wave is traveling to the left. That is the negative x direction. So we would use plus in the equation. And the rest of the equation, you can figure out exactly the same way we did earlier. Fill in everything else, choose any crest or trough from either graph to fill in to find phi using the total phase. So everything else is pretty much the same. You just need to use this somewhat different setup to figure out the direction of travel.
So if we were given two y versus t graphs instead, we basically use the same process.
Yeah, same idea. It's going to be slightly different in the sense that going back to the definition of speed, if you have two time graphs, then you'll know the distance between them based on the x values, and you'll be solving for delta t. But you'll still be looking for like a trough on one graph and a trough on the other graph that are that amount of time apart from each other. And once you've established this trough hits this location at this time and this other location at this other time, you can still draw exactly this sort of diagram we just did and figure out which one happens earlier, which one happens later. So as soon as you've established the coordinates of the same trough twice, the procedure is exactly the same from that point onwards. Any other questions? All right, get some practice on that. Give that a try with the other examples you've got, and I will see you next time.
Thank you, Casey.
You're welcome.